Hi there, in this video we're going to go over the duality of the Fourier transform. Now we had looked at this in a previous video but we never went into any detail, so let's have a little look at it now. So the idea is that if you have some function of time, okay, so let's call the function small x of t, and let's say we let the function as an example equal 1. When we do the Fourier transform of that, we end up with a function of frequency. We call it big X of j omega, and in this instance here that would be a delta function, okay, so that would just be delta omega. Now the idea of the duality is that if we then take that function j omega and put it back into the time domain, so now you'd end up with big X of jt. Okay, so we'll take that function there, which is the impulse function in this example, so that's delta t, and if we find the Fourier transform of that function, then we go back into the frequency domain j omega, and that gives us a function which is similar to the function we started off with, x of t, but its x of t is going to be scaled by 2 pi, so we get 2 pi x, and it's obviously no longer t, it would be j omega, but it isn't j omega, it's actually minus j omega. Okay, now the duality, as you can see, tells us that this function here is of the same type as that function, this function here is of the same type as that function. Okay, so we're taking the Fourier transform of a function, we're getting another function, we take that function back in the time domain and we do the Fourier transform of it again, and we get back to the original function, but a scaled function, also inverted by a factor of -1. Now we can make the statement of the duality if we say we have a function x of t, and that gives us a Fourier transform x of j omega. We then take our x of j omega back into the time domain, so it becomes x of jt, and that then gives us Fourier transform, which is a scaled version of the original transform multiplied by -1 in the omega axis. So that there is the statement of the duality of the Fourier transform. So now what we'll do is we'll go ahead and we'll prove that that's the case. Now we want to be able to distinguish between this omega here and that omega there, okay, and you'll see why we need to do that whenever we work through the proof. So we'll make a substitution, we'll call that axis, rather than calling it omega, we'll call it lambda. Okay, so that's a lambda axis and that's lambda. Okay, so it's still frequency, but we're just giving it a different name to distinguish it from this particular frequency axis here. Okay, so we're going to go through and we'll find the Fourier transform. So what we can say is, we can say x of j lambda is the integral from minus infinity to infinity over function x of t times e to the minus j lambda t by dt. Okay, so that's our first Fourier transform, going from here to here. Now we're going to go from this axis here to this one over here. So we're going to do our second Fourier transform. So the second Fourier transform, okay, it tells us our function, let's call it small x of j omega, is the integral from minus infinity to infinity. Now the function we're going to use is x of j lambda, so big X of j lambda. Now remember that lambda now is still a time, okay, so we haven't actually replaced it by the value of t, okay, we've just kept it the value of lambda, but lambda is no longer a frequency, lambda is now a time. Okay, so that's x of j lambda times, it's going to be e to the minus j omega, now no longer t is now called our lambda, and we're going to be integrating with respect to, well, no longer t, value lambda. So we've got two functions here, and it goes from time to frequency to time back to frequency. Okay, so what we can do is, we notice that that x of j lambda, well, that there is just this here. Okay, so it means that we can take this function here and place it in here. Okay, so then we'll end up with x of j omega equals, well, we'll write this out first, so it's the integral from x of t e to the minus j lambda t by dt. Okay, and that's minus infinity to infinity. So that's this point here. Okay, and then we'll replace the rest of it here, which is times e to the minus j lambda by d lambda. Okay, and it's the integral from minus infinity to infinity. Okay, so that's us written out in full, but it can be simplified now, as we can take that, we can have the minus integral from minus infinity to infinity, and if we can take the x of t out, okay, x of t is not a function of lambda, okay, so it can get taken outside one of the integral signs. So we're going to have x of t, and we'll have the integral from minus infinity to infinity of what's left. Now what's left there is, well, it's going to be 1, because we think about it as 1 times, and we'll have e to the minus, and we'll bring these together, so we've got minus j lambda t and minus j, and I've missed out the omega there, minus j omega lambda. Okay, so there should be an omega there as well from here. Okay, so it's j omega lambda. So we're taking out the factor, write this again, we've taken out that factor lambda minus j lambda. Okay, and we're just going to be left with our omega plus t, omega plus t. Okay, right, and that's by d lambda, and of course the last one here from this integral is by dt. Okay, so we can kind of take a wee bracket, put a wee bracket around that bit there. Oh, take a bracket, put it around that bit there. That's a bracket, put it around that bit there. Now this whole thing here, that thing that I've bracketed, we can rewrite that, and we can write this whole thing as the integral from minus infinity to infinity of x of t. Okay, and we'll leave this dt here at the end, dt. Okay, now everything that's inside this bracket here can be written as, and I'll explain this after I've written it, but you may well notice it if you looked at the previous videos, would be 2 pi delta omega plus t. Okay, I'll just move that up a bit. Okay, that's by dt by dt. Okay, now you can see that there is equal to this here, because we know that if we found the Fourier transform of 1, that Fourier transform of 1 gives us 2 pi, say our value, just call it delta x. Okay, so and that's what we're doing up here. We're taking the Fourier transform of 1, so it's 1 times e to the minus this thing here, okay, by d lambda. Okay, so that there is just the Fourier transform, but we're replacing our values, our value t, by t plus w. Okay, so that's just the same thing as replacing this here by x by, say, x plus some other value y. Okay, so that's all we have there. So if you just remember this here, okay, and you can remember to get that Fourier transform, you just did 1 times e to the minus j, whatever the value was. Okay, so but that gives us this here. Okay, so it means that what we can then do is we can take the value of 2 pi out, 2 pi, and we do the integral from minus infinity to infinity over, and that's going to be x of t, and it's going to be delta omega plus t by dt. Now we can look at this here, and that's going to give us our value 2 pi times delta, but it's going to be delta, it's going to be omega, I get that from there, so it's going to be 2 pi, and it's going to be our function there, so it's going to be x of minus omega. Okay, because all that there is the shifting property of the delta function. Okay, so the delta function there is going to take out the value of x at the point omega. Okay, but it's going to be minus omega because the shifting property would tell us it would be, say, delta t minus t naught times x of t, would just be the value of x at t naught. Okay, so we've seen the shifting property in a previous video. So if we've got the t plus t naught, then the value that we take out would be x at minus t naught. Okay, so that gives us this value here, 2 pi x of minus omega. So that whole thing then can be rewritten, and we can see that that whole thing is just what we've got up here. Okay, so we now have a factor of j, so we say x of jt, so if we had x of jt would equal 2 pi x of minus j omega. Okay, so that's the little proof there. I'll do another video, and at some point I'll go through a few examples of using that. Okay, so thank you for listening, and goodbye.